She's an undergrad student at UCLA, so wow, it's really nice. And then she's a part of the citizen science program project, Panoptes. And then today she will be presenting progress on the new web-based astronomy tool she works on this summer. Please take it away.
Hey guys, can everybody hear me?
Yeah, great.
All right, cool. So thanks for the introduction. I'm gonna go ahead and start with a bit of background. So Project Panoptes is a global citizen science program with the goal of discovering transiting exoplanets that have a dip in brightness on the order of around 1%. And to do this, we're building a worldwide network of low-cost robotic telescopes called Panoptes units. So Panoptes units look like this, and there's a lot of different parts, but the most important things that you need to know are that it has 2 DSLR cameras on a computerized equatorial mount. And this is used to image the night sky in 10 by 15 degree chunks, which each contain tens of thousands of stars. And there are also a number of sensors on board, like for monitoring weather over here. There's a cloud sensor, an anemometer for wind, thermometers, and humidity sensors that it uses to take measurements of its surroundings. Also, there's an accelerometer in the camera box circuit board, which is shown, here's the camera box and this is the inside. Here's the circuit board. And the accelerometer can tell us the unit's orientation. And all data from these units, including its observations of the sky and its sensor data, get uploaded to our Google Cloud database. New slide is not working. Oh my God, it went to the end of my talk, sorry. Okay, so here is an example of a picture taken with a Panoptes unit. And this is the comet from earlier this summer. So you can see that for a telescope, it's got sort of a big field of view. And so these units are designed to be low cost, under $5,000 to build, and can be built by pretty much anyone, like students, amateur astronomers, and members of the public all around the world. And some of the most recent units have actually been built by students in Italy, the US, and Bhutan. So after a unit is built, it gets deployed in a permanent remote location, which can be far away from cities. And here's a couple of examples of remote units. So this one is Pan 1, and it's all the way on top of Mauna Loa in Hilo. And another one deployed in a remote location is Pan 12, which is on Mount Wilson in California. And this is a unit that I helped to deploy last summer. And actually, I helped manage the observations on this unit for the past year. So right after Pan 12 was deployed, I spent about a month having it observe known transits, and I was actively picking targets from a database. And with the iObserve app, I would take time every night to visualize the target, where it was in the sky, when the transit started and ended, how high up it was, and how far it was from the moon. And so I had a pretty good handle on where each target was. And for me, it was exciting, but time consuming to plan the observations, then get on sky, and then have to SCP over the initial images to check the exposure time, and then watch out for any errors when observing through the night. But since then, we set Pan 12 to pick its nightly targets from a pre-made list of Northern Hemisphere test sectors. And after I hit start on the unit, it handles all the calculations and optimizations to find ideal targets for days or weeks on end. The problem is the list of targets is super long, with dozens of targets all over the sky. And with a busy schedule, it's not really possible for me to go through and figure out like where each of these sectors were. And so now I've sort of lost out on having an intuition for where the unit's pointed. And this is unlike when I had to pick the targets manually. And besides photographing a few comets, I didn't really feel as that engaged in observing over the past year. I only SSH on the unit onto the unit occasionally to check for errors. But getting some personal experience with the whole Panoptes observing workflow made me appreciate that people who operate these units remotely need an easy way to, number one, see the unit status and know when it needs maintenance, and number two, stay engaged in its observations even when they're automated. So, so one of the ideas we had for making it easier for people to see their data is we got the units set up to post updates to their Twitter accounts. They haven't really gone viral yet, but it's at least nice to be just like scrolling through Twitter and then randomly just see what your unit's up to. Also, we're working on some web apps to make Panoptes data more accessible. And the first is the Panoptes Data Explorer, which lets you both view and download data as it comes into our Google Cloud database. And the second web app is something that will let people view and schedule observations across Panoptes units worldwide. And it uses the open source Tom toolkit that's by the Las Cumbres Observatory. And in addition, we've been working on a 3D visualizer that can create a lightweight, stylized simulation of real-time telemetry for any given Panoptes unit. So now I'm gonna go ahead and do a demo of that. So here's how it looks. And so the mount can move around based on the accelerometer readings from the camera box. So we can see how the unit's pointing. And in addition, the sky is dynamic and can change based on the sun's altitude. So it can fade from day to night and then the stars will come out. And the stars can change with the unit's latitude, as can the mount's adjustment. And so you can see a couple of pretty well-known constellations. So Orion's over here with Betelgeuse, and there is Taurus, and there's the Pleiades. The star data comes from the Magnitude 5 Star Catalog by Dr. John Pratt, and it's a subset of the Yale Bright Star Catalog, and it contains almost 4,000 stars. Also, the simulator can demonstrate like what the weather is at the unit's location. So here you can see that you can toggle like whether there's clouds up or not, and this can definitely get fancier later on to show like more different levels of cloud cover. And all in all, the simulation is pretty lightweight. It's compatible with modern browsers, and it's been tested on multiple Android and Apple mobile devices where it gets fluid animations of upwards of 20 frames per second, depending on the device, which is good. And it hits 60 frames per second, which is like the max for a web browser, even on a Chromebook, which is something that students may be using. So some of the tools that I used to help make this were, first of all, Photoshop and also the Procreate app for iPad. I used it to make some of the concept art and the image textures. Blender was used for 3D modeling, texturing, and exporting the files. And JavaScript was used to create the app. Specifically, we used the 3JS JavaScript library, which makes it easy to do WebGL stuff at like a higher level. And also, it makes doing VR stuff pretty easy. So I was able to easily port the app into VR. And so this demo, I'm using an Oculus Quest headset to look around the scene and also move around it. This headset can measure both where you're looking and where you are in physical space. And it's also been tested on, it's compatible with your phone and like any VR headset like a Google Cardboard display, which are pretty affordable. And we think that this type of VR app can be useful both for outreach events at like schools, and also we have a museum exhibit at Imiloa that this could be a part of in the future. So as for what's next, we're envisioning this as being part of like a dashboard of some sort that shows all unit information, like current target, weather conditions, and forecast, and plots of sensor readings over time. And we're working on how to integrate this along the Data Explorer and Scheduler. And we're trying to modularize the code into smaller individual components. And part of the reason is so that we can load and discard things easily from the scene. And this will allow us to have features like various environments that the units can be placed in, which can help units stand out from one another on the website, because the simulator otherwise would look pretty much the same, maybe except for time of day. And so here is some of the initial concept art. So that's all I have. And if you're interested, you can sign up for email updates on Panoptes 3D for when it releases and gets new features, and when we start doing beta testing. And if you'd like to learn more about Project Panoptes or get involved, you can check out our website at projectpanoptes.org. Thank you very much.
Yeah, thank you, Therese. That's really amazing. It's a really nice talk. So I guess that some people that typing their question for you. So then maybe as a chair, I'm going to ask you that maybe the simplest or easiest question. So I think again, this is really amazing. So then actually you mentioned a little bit, but then how you can what's the next step, and then what's the target of your observers or user of the apps?
Do you mean what's like the next thing I'd like to do with this?
Yeah, right. And then that's kind of one question. And the next question is that maybe what would be a target observers or a user of the apps of the.
Oh, okay. So the next thing I'd like to do is probably get this connected to our database. Right now, as you can see, I was kind of just like dragging sliders around, which change values that we would, which we're going to be getting from our database. And so that would be really exciting for me to be able to see like actual data coming in from our units visualized in the 3D visualizer. The people who I expect to be using this, honestly, I feel like anybody could use it, because it's not like a game or anything where like only young people would know how to install it or know where to look. Like I think anybody with a phone or with a computer who wants to monitor their unit would be the target audience. And even people who don't have a unit and they're just curious about like what are the Panoptes units in the network up to right at this moment.
I see, yeah, cool. Right, and then the next question is that's really neat. Does the 3D viewer allow viewing different location telescopes and what they are doing?
It's depend. If I understood the question correctly, it will change based on people's units locations. So something else that I need to figure out is I need to start getting in like actual astronomy data into the app to dictate like at this particular location which stars are overhead, and also things like the phases of the moon, locations of the planets, and the locations of the sun, and things like that. That's another thing I actually have to figure out. Some of it can be like pre-computed, and then other things I might have to use like some sort of API. But yeah, it can definitely change based on where your unit's located.
Great. So then the next question is what connection are available to upload data from the unit to Google Cloud at a given site?
So it just needs an internet connection. There's a script that runs. So there's a control software that basically handles all the observations autonomously. And at the end of it, it's programmed to gather up all the data and just upload it to the cloud. But things like sensor readings are updated on the cloud every few seconds, so much more frequently. And so yeah, all you need is the internet connection.
Okay, great. So then I guess let's thank Therese again.